Hello, this is Rohit from IIT Madras, India. In this poster presentation, I will talk on how to efficiently enhance low-light image with unpaired supervision using generative adversarial network. Enhancing low-light images is crucial for improving visibility and reducing issues like noise, color distortion, and poor contrast. These degradations reduce the performance of high-level visual tasks. To create an effective real-time low-light image enhancement model, we need high restoration quality, that is, reduced noise, great detail, vibrant colors, and better visual appeal, along with fewer parameters and low latency. But it is highly challenging to train such a model with a low light and normal light image pair, where they are considered input and ground truth respectively in a supervised training. As it is challenging to simultaneously capture a low and a normal light image pair of the same scene, we focus on proposing a highly accurate and computationally efficient model trained with unpaired images. Our contribution is sixfold. Our method offers training with unpaired settings, allowing us to train with diverse images and generalize exceptionally well on real-world test images. We propose a simple yet effective three-layer U-type hierarchical generator network that employs parallel processing on the encoder side. We feature a self-regularized illumination attention map that prioritizes darker regions for balanced image enhancement, avoiding overexposure and underexposure. We also propose a modified residual dense block, assuring a lesser parameter count and reducing the information loss during non-linear rectification. ELEGAN surpasses baseline methods in improving the quality of low-light images, as confirmed by visual analysis and no reference image quality assessment. We provide a performance comparison of our method against state-of-art methods, showcasing the inference time taken for each of the methods. In contrast to a typical UNet architecture, our approach involves skipping intermediate scales and focusing the majority of computation on higher scale spaces with lower resolution. Our three-layer U-type encoder-decoder generator eliminates interdependencies between encoder layers, enabling each layer to operate directly on the input image. This parallel operation of encoder layers reduces idle time, resulting in faster execution. Unlike an attention map based upon an illumination map, we propose an attention map dependent on the maximum and minimum intensity values of the three RGB channels. We adopt a self-regularized illumination attention map as computed in equation 1 for a guiding mechanism within the skip connections. The original residual dense block does non-linear rectification, and thus the negative values of feature maps are irreversibly lost. Additionally, the swift growth of number of channels in residual dense block leads to large block parameters and computation. Reducing channel count is an obvious way to reduce the parameters and computational overhead. We propose a modified residual dense block which aims to infuse the CNN with sufficient non-linearity for low-light image restoration by preventing rectification of the output at each convolution layer. Also, the modified residual dense block reduces parameters by compressing channel in succeeding feature maps using 1x1 intermediate convolution layer. The last pointwise 1x1 convolution layer, unlike residual dense block, sees the non-rectified output of all previous layers, thus avoiding information loss due to non-linear rectification. This is the overall architecture of the attention map guided three-layer U-type generator network. As discussed, our generator avoids computational overhead at the lower scale of the network by operating at three different levels of feature resolutions. The subsequent encoder layer is provided a downsampled image using pixel shuffle by a factor of 4. Pixel shuffling, unlike conventional downsampling method, retains the feature information. This parallel operation at the encoder layer reduces the idle time, thus speeding up the execution process. More convolution layers are assigned to the 1/4 and 1/16 encoder feature resolution level as they operate at the lesser resolution. Inspired by Xiang and others, we incorporate a combination of image level global discriminator and a local discriminator, both using patchcan. The local discriminator learns to discriminate between real and fake by using local patches randomly clipped from real normal light images and fake enhanced results respectively. The dual discriminator structure ensures that all local patches of enhanced result resemble normal light images, thus preventing under or overexposure at local level. Like Xiang and others, we employ the self-feature preserving loss to preserve the image content features to itself before and after the enhancement as in equation 8, where IL denotes the input low light image and GIL denotes the generator's enhanced output. Phi denotes the feature map extracted from a VGG16 model retained on ImageNet. A similar self-feature preserving loss is used to regularize the cropped local patches from real and fake images for our local discriminator. The overall loss function for training ELEGAN is given as in equation 9. As shown in equation 2 and 3, the relativistic discriminator structure is used as a global discriminator to estimate the likelihood of the real data being more realistic than fake data, and to instruct the generator to create a fake image which is more realistic than real images. Here, C denotes the network of discriminators. XR and XF are samples of real and fake distribution. Sigma represents the sigmoid function. Like Xiang and others, we slightly modified the relativistic discriminator by replacing the sigmoid function with the least square GAN loss. Finally, the loss functions for the global discriminator D and the generator G are given in equation 4 and 5. For the local discriminator, we randomly crop 5 patches from the generator output and real images each time. Here we adopt the original least square GAN loss as the adversarial loss, as shown in equation 6 and 7. Our training and test dataset mixture is as shown. For training, we use 914 unpaired low light images and 1016 normal light images. For qualitative evaluation, we use synthetic as well as 4 real-world datasets. We use 4 no reference image quality metrics. We perform visual analysis by comparing the proposed method with 4 state-of-the-art methods, namely SCI, URetinexNet, EnlightenGAN, and UNE, as shown in figure 6. The enhanced image recovered by UNE is weakly illuminated and is unable to extract the details in dark region efficiently. SCI causes overexposure of artifacts and blurs, which distorts the result and makes them blazing with information. URetinexNet under-enhances the color, results in color distortion, and has noticeable noise. As observed from the figure, our method preserves contrast and details in a better way as compared to EnlightenGAN. Image IDs 1 to 5 are assigned to the 5 image samples in figure 7, top to bottom. Our method enhances dark regions for images 1 and 2 and preserve the image colors and details simultaneously in both focused and out of focus regions. In contrast, EnlightenGAN fails to preserve color and over-smoothens the detail for image 1 and 2 respectively, while other baseline methods amplify noise and even produce color deviation. As opposed to other baselines, ELEGAN provides outcome with adequate contrast, vibrant colors, and minimal noise as shown in image 3, 4, and 5. Compared to the existing low light image enhancement method, we specifically recover image with reduced noise, great details, vibrant colors, and better visual appeal. The 5 image samples as shown in figure 7 are assigned image IDs from 1 to 5, and their corresponding performance score on 4 image quality matrices for baseline methods is shown in table 1. As evident from table 1, we achieve better performance on most metrics for different image samples. This highlights a good performance in structural recovery and illumination restoration. The PIQE score for various methods on 4 datasets is shown in table 2. ELEGAN performs best in all 4 subsets and overall average PIQE score, thus affirming its superiority over existing state-of-the-art methods in producing high-quality visual outputs. Figure 8 compares the performance and efficiency of ELEGAN and state-of-the-art methods. We perform efficiently in both computational time and performance score with respect to the state-of-art. The inference time taken per image for our model is approximately half that of EnlightenGAN while achieving a lesser PIQE score, thus affirming that our model excels in both output quality and computational efficiency. Thank you.